Hi there. Let's look at topic 2 in our Science 9 unit on chemistry. And we're going to look at atoms, atomic theory, how we might draw an atom of different substances, as well as what happens to atoms when they're mixed in a chemical reaction. So to understand what an atom is, we need to talk about, subatomic particles. Atoms are made up of three things. They have protons, which carry a positive charge and they're located inside the nucleus. Neutrons, which carry no charge, and they're also inside the nucleus of an atom. And then electrons, which are negatively charged, and they're located outside of the nucleus. So these three subatomic particles help make up what an atom is. And by definition, it's the smallest component of an element having still the chemical properties of that element. So let's talk about how we might draw an atom of a substance. For example, neon, its atom might look like this. It has 10 neutrons in the nucleus, 10 protons, and then it has 10 electrons outside of the nucleus in different orbits or energy levels. Here's what lithium would look like. 1, 2, 3 neutrons, 1, 2, 3 protons, and 1, 2, 3 electrons. So, how do we know how many protons, neutrons, and electrons are in an atom? Well, let's do that. We'll deal with the periodic table a little later on, but the periodic table helps us tell how many protons, electrons, etc. So when we look at the periodic table, for example, we notice that boron is number 5, carbon is number 6, nitrogen is 7, oxygen is 8, etc. These numbers are called the atomic number, and they stand for the number of protons in an atom of each of these substances. So let's take fluorine, for example. It's number 9 on the periodic table. So let's see if we can draw out an atom of fluorine. So we draw a circle to represent the nucleus. 9 stands for 9 protons. Now atoms are stable. Their overall charge is 0, which means in the case of an atom, unlike an ion, if it has 9 protons, it will also have 9 electrons. So we have to fit 9 electrons outside of the nucleus. And according to the Bohr model of what an atom might look like, he talked about electrons occupying certain orbitals around the nucleus. And these orbitals only have certain size and energy level. So 2 electrons is all that would fit, even though there are 9, in the first orbital around the fluorine atom. So we still have more to go, and so we have 7 more to make 9. So 7 electrons would be arranged in the next energy level. And that's it, we're done. Incidentally, it would actually fit 8, a total of 8 in this one, and then if we're past that, we have to go to the next one, and this would fit 8. And how do we know this? Well, there are 2 elements on the periodic table in this row which help us remember, or we call it a period, that there are only 2 electrons in the first energy level. There are 8 elements, 1, 2, 3, 4, 5, 6, 7, 8, and that helps us remember 8 electrons in this energy level. There are 8 elements, 1, 2, 3, 4, 5, 6, 7, 8 in this one, so that means we could fit 8 in this one. And if we had to go to another energy level, we could fit 16 and 16 and 16. So that helps us tell how many electrons will fit in each of the orbitals. I'm not quite done yet. So I have 2 electrons and 7 electrons. There are 9 electrons in these two energy levels. And incidentally, we call this outer one the valence shell. That's the outer shell. And it's most heavily involved in bonding when it forms a compound. So the valence electron isn't shielded like these ones, and its influence is how reactive the atom is in joining up with other atoms to form something called compounds. Okay, how many neutrons? Well, to find that out, we need to look at a second thing on the periodic table, which is its relative atomic mass. So in the case of fluorine, it's 18.995, and we would round that to 19. Now, a lot of these elements have what's called an isotope, which means another form of its atom, which may or may not be stable. So to get the atomic mass, we add up or average all the different isotopes. So in our case, 18.995, we round to 19, and we take the atomic mass, or the relative atomic mass, we round it, 19, and we subtract it by the number of protons, which is 9 on the periodic table, and that gives us 10. This stands for the number of neutrons. So fluorine would have 10 neutrons in its nucleus. Next, I want to talk about atomic theory, because over time, our understanding of what this tiny little thing called an atom might look like has evolved from an earlier gentleman called Thomson and his plum pudding model to a Rutherford model of what we thought the atom looked like, to the Bohr model, which is what we use today to draw an atom, to the most recent, which is called the quantum mechanical model or the cloud theory. So let's look at Thomson. Thomson thought that atoms were kind of like, the analogy used was raisin bread or plum pudding model, such that electrons were kind of stuck around the nucleus or pushed like raisins in plum pudding. And this was kind of a jello-y like substance, and the positive protons were located sort of and made up the pudding part, and the raisins were stuck around like that. Then we moved on to Rutherford's model, and he sort of thought that the nucleus was like the sun, and electrons orbited the nucleus, and that's how they were located. But there was something sort of missing here in that they don't speed up and radiate energy. Sometimes we know that these electrons will move orbits, and his model didn't account for that. So Bohr came up with this next one, and if we look at this, we could figure out what atom this was. 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. So there are 7 protons, there are 7 electrons, and so we could go to the periodic table and identify this substance, which would be nitrogen. So this would be an atom of nitrogen due to its chemical makeup. Oh, and of course, here it is, nitrogen. So we use Bohr today to help us draw on paper two-dimensional models. And remember, the outer shell is called the valence. And 2 electrons fit here, and we can fit 8 here if we had to, and then 8 more if we had to. So the valence shell is very important when it comes to chemical reactivity and whether it'll react with something else. The final model is the quantum mechanical model, which indicates that electrons aren't as predictable as Bohr had said, and they sort of float around and they occupy kind of a cloud depending on their energy and so on. So it's hard to draw what an atom looks like according to the cloud theory, so we use Bohr's model. So here's what the periodic table of elements looks like with all its atoms, and you should notice as we go down the table, the size of the atoms get bigger, and these elements get more reactive. So let's see if we can draw a few more. Let's say we have to draw a chlorine atom. So what do we need to know? We need to know what it is on the periodic table. So chlorine is number 17. What does that stand for then? It's got 17, I'll draw it down here, 17 protons in the nucleus. We don't know how many neutrons yet, but we'll find that out. Now, because it's an atom and not an ion, it's stable, which means it's got 17 electrons. So we can, let's fit them in there. 2 electrons here. So I've got 15 more to go. Let me draw a circle for the nucleus. We can put 8 electrons. So I've only got 7 more to go. And so I'll put the last 7 electrons in this shell, and we're done. Let's find out how many neutrons. Let's go back to the periodic table. Chlorine is 35.45. So 35.4, we round to 35, minus 17 protons gives us 18 as our number of neutrons in the nucleus. Let's finish this with a quick video on atoms. If I can find it, let me go to Explorer, not that page, not that page. There it is. And let's push play.
This will be followed by electrons. And the third and final program in this unit will be on conduction itself. But our story begins with atoms. We know that everything is made up of molecules. That tree, the plastic cup, the magnifying glass, this piece of lead pipe. Even you are made up of molecules. Does that mean that molecules are all the same? In that case, why do glass cups break when you drop them, when plastic ones don't? On the other hand, why can't you see through a magnifying glass made of pink plastic? Or chop down an aluminum tree with a rubber axe? If all these things were made of identical molecules, how could they all be so different? If everything around you were constructed with exactly the same building blocks, it'd be like living in a world of Lego. So molecules can't all be the same, can they? What are molecules made of anyway? We know that they're little lumps, but little lumps of what? Of course, there's no magnifying glass powerful enough to let you see molecules. They're much too small for that. But scientists now know that if by some miracle you could look closely enough at a typical molecule in plastic, for instance, you would see that it isn't a solid lump at all, but a lump of thousands of tiny round things all jiggling about together like a bunch of grapes going bananas. Scientists call these tiny round things atoms. But notice that not all the atoms are alike. Some are big and some are small. Some have a lot of mass and some have very little mass. Now let's look at a typical molecule in glass. It's completely different from a molecule in plastic. There are only 3 atoms instead of thousands.